Okay, so in this video, we will talk about the self-inductance and the energy stored inside an inductor. So, this is a coil. Okay, this is a coil, and then this coil is connected to a battery. Please explain the phenomenon of self-induction. Self-induction occurs when the current flowing in the coil changes. The magnetic field produced by the current also changes. Therefore, the magnetic flux linkage in the same coil also changes. And therefore, there is an induced EMF in the same coil. Okay? Because you know that from the Faraday's law, the EMF induced is directly proportional to the rate of change of magnetic flux linkage. So when you know that there's a change in the magnetic flux linkage, there must be some induced EMF. Okay, so if I want you to define the self-inductance L, this would be your answer. Induced EMF is directly proportional to the rate of change of current. And then this constant is called L. Okay, I use a negative sign here. Okay, because when the current is increasing, then the direction of the induced EMF is opposite to the current. But then when the current is decreasing, then the EMF is in the same direction as the current. But then I will tell you this later on. Okay, so trust me that you have a negative sign right now. Okay, so L equal to negative E over di dt, where E is the induced EMF in the coil, and then di dt is the rate of change of the current in the same coil. Okay, so L is in self-inductance. Okay, so for example, if this is a solenoid, okay, if this is a solenoid, please derive the self-inductance of the solenoid. Okay, so you know that the magnetic flux density of the solenoid is mu naught Ni, where N is the turn density, okay? It's the number of turns over L, where L is the length of the solenoid, okay? So this is the magnetic flux density inside the solenoid. And then, okay, the magnetic flux linkage of the same solenoid is N-phi, which is MBA, okay? And then you still remember that from the Faraday's law, you know that E equal to negative dN-phi over dt, okay? Because when you are considering the Lenz's law, you have to put a negative, okay? So you know that back EMF is negative dphi over dt. But then, just now when I introduced to you the definition of the self-inductance, you know that back EMF equal to negative L di dt. So you know that E equal to negative L di dt equal to negative N dphi over dt. Okay, so you know that Li equal to N-phi. Okay, L is the self-inductance, I is the current, N is the number of turns inside the solenoid, and then phi is the magnetic flux. Okay, so you know that Li equal to N-phi, and then you can get L. Okay, so now you have already derived the self-inductance of a solenoid. Okay, so for example, if this is the coil, and then maybe the coil have n turns, okay, but maybe the coil has only one turn, okay, which I don't care. You really have to know that one coil can have many turns. Okay, so this is the switch, this is the battery, and then this is the resistor. Okay, so at t equal to 0, the switch S is turned on. Okay, when t equal to 0, the switch is turned on. So you know that the current in the coil rises. Okay, that means that the current in the coil increases from 0 to a upper limit value. Okay, so at this time, you know that di dt is greater than 0 because I is increasing, so di is greater than 0. So you know that there's a negative sign in the back EMF. So you know that negative times a positive value equal to a negative value. So you know that the direction of induced EMF is opposite to the direction of current when the current is increasing. Okay, at time equal to t2, switch S is turned off. That means that you open the switch S at T2. The current in the coil drops very fast. Okay, just now the current rises slowly, now the current drops so fast. Okay, so you know that di dt is less than 0 because I is decreasing. So you know that di is less than 0. So a negative sign times a negative value is a positive value. So you know that EB is a positive value. Therefore, you know that the direction of the induced EMF is the same as the direction of the current. Okay, so by looking at these two diagrams, you know that when you switch on the switch, that means that when you close the switch, the current will rise. And then when I is increasing, di dt is positive. So you know that the back EMF is a negative value. Between T1 and T2, you know I is a constant. So di equal to 0. So you know that EV is a 0. When the switch is opened at T2, you know that the current drops so fast. So di dt is a negative value. Therefore, back EMF has a positive value. Okay? And then you notice that the steeper the graph, that means that the steeper the gradient, the larger the back EMF. Okay? That means that, for example, here you know that it drops so fast, you know, because the gradient is so steep. Therefore, the value is so large. Okay? For example, here, the gradient is also quite steep, but then not as steep as here. So you know that the value of the back EMF is here. Okay? So you notice that the largest back EMF can only be obtained when you switch off the coil. Okay? When you switch on the coil, you cannot get so high back EMF. Okay? So now we want to know how to get the energy stored inside an inductor. Actually, in your syllabus, you are only required to memorize U equal to half Li squared. Okay, so if you don't want to learn about the derivation, it's okay. But then I need to tell you, okay? So, okay, you recall that in the video 13.1, when you are trying to derive the energy stored inside a capacitor, that means that you will get half U equal to half CV squared equal to half QV equal to Q squared over 2C. You are actually saying that the capacitor stores the electrical potential energy in the form of electric field. And therefore, for this parallel plate capacitor, you know that the energy density is half E naught E squared. Okay, and then you get the total energy of the capacitor by multiplying the energy density times with the volume. Then you can get half CV squared. Okay, then by using Q equal to CV, then you can get half QV and Q squared over 2C. Okay, so you remember that for a capacitor, it stores energy in the form of electric field. But then, for an inductor, the energy is stored in the magnetic field, okay, because it stores magnetic potential energy. So for example, if the current is moving in a solenoid like this, you already know that from the north pole, you can see the current is moving in an anti-clockwise direction, and then for the south pole you see that the current is moving in a clockwise direction. Okay, so the energy density of the magnetic field inside the solenoid is B squared over 2 mu naught, and then the B, which is the magnetic flux density inside the solenoid, is mu naught Ni. Okay, and then you multiply the energy density with the volume, then you can get the total energy of the solenoid. And then what is the volume of the solenoid? The volume of the solenoid is area times the length of the solenoid. Okay, therefore, and then you also know that the mu naught N squared A over L is what? Is the self-inductance of the solenoid. Okay, because just now you already derived the self-inductance of the solenoid. Okay, so you know that the energy stored by the inductor is half Li squared, okay, where L is the self-inductance and then I is the current. So please describe how an inductor stores energy. When the switch is turned on, the current rises from 0 to a non-zero value. And then during the rising of the current, you know that an induced EMF is produced and is against the direction of the current. Okay, because just now you already know that the direction of the induced current is opposite to the direction of current when the current is rising. Okay, so you know that the direction of induced EMF is opposite to the direction of current. So the induced EMF opposes the rise of current, and then when the current continues to rise, work is done by the EMF of the source against the induced EMF to establish the final current in the inductor. So this work done results in the conversion of electrical energy to magnetic potential energy in the form of magnetic field inside the coil. So when the switch is turned off, the current drops to zero, and then the magnetic potential energy is converted back to electrical energy. And then you have to remember that in the next chapter, which is the alternating current, you know that actually a capacitor and an inductor cannot dissipate energy, because whatever energy you gain, you have to give it back to the circuit later on. Okay, so for the alternating current, the inductor cannot dissipate energy. An inductor of self-inductance 2 Henry is connected in series to a battery of EMF 6 volt and a vibrating switch. A neon lamp which needs minimum voltage of 100 volt to light up is connected parallel to the inductor. Okay, that means that you know that this is the lamp. Okay, this is the neon lamp, and then it is connected in parallel with the inductor. Okay. So the variation of current through the inductor with time is shown like this. Okay, so is it very familiar to you? Okay, because you have already learned it just now. Okay, so you know that when you get the current graph like this, your back EMF will look like this. Okay, so the switch is closed at t equal to 0 second and open at t equal to 1 second. Please determine the resistance of the inductor. Okay, V equal to IR, where I is the maximum current. Okay, because this is the real current. Okay, you know that the current cannot simply straight away jump to the maximum value because there is self-inductance, because there is a back EMF. Okay, so V equal to IR, and then you can get the R. Give a reason for the delay in the current to achieve the maximum value after the switch is closed. That means that why the graph does not straight away start from here. Why it have to start like this? Why the current have to rise so slowly? Okay, because when the current in the coil is rising, the coil has a changing magnetic flux, and then this produces an induced EMF opposite to the battery EMF and causes the delay. Okay, because of the back EMF. Okay, sketch a graph of the variation of induced EMF in the inductor with time. Okay, so you already know how to draw the back EMF versus time graph. Okay, because you only use the back EMF equal to negative L didt. Then didt is what? Didt is the gradient, right? So when you find out the gradient and then you multiply it with a negative sign, so you can get this graph. Okay, so you have to remember that when it rises very steeply, then the back EMF has a very negative value. But then when the gradient gets less and less, then the value of the back EMF is becoming less and less negative. When I is a constant, di is 0. When didt is a very negative value, but then when it times with a negative sign, then the back EMF has a very positive value. When the current is decreasing slowly and slowly at the end of 1.02 second, okay, because the gradient is getting less and less, then you know that didt is a less negative value. So when it multiplied with the negative sign, then it is a very small positive value. Okay, so this is how you convert this graph to this graph. Okay, based on your graph in 3, which is this graph, explain how the neon lamp can be lighted up. Okay, so just now you already know that the neon light will be connected in parallel with the inductor. So when the potential difference across the inductor is maximum, then the potential difference across the neon lamp is maximum, because you know that the potential difference across here is equal to the potential difference across here. Okay, so I think this is connected to a battery here. Okay, so when the switch is open and t equal to 1 second, the current decreases to 0 very fast. So the rate of change of current is very high. So this can produce a very high induced EMF, which can light up the neon lamp. Okay, because you know that the maximum back EMF is here, which is when the switch is open. Okay, so when the current drops so fast, then only you can get a super high EMF. Then only you can exceed the minimum voltage of 100 volt in order to light up the neon lamp. Calculate the initial rate of change of the current when the switch is closed. Okay, when the switch is closed, you know that it's at time equal to 0. Okay, so you have to find out didt at this position. Okay, so E equal to L didt. E is what? Back EMF is 6 equal to 2, because the self-inductance is 2 Henry didt. Therefore, you can know that the didt is 3 ampere per second when it's at this position. Okay? Calculate the average induced EMF E in the inductor when the switch is open. Average E when the switch is open is in this region. So you know that 2 ampere decreases to 0 in 0.02 second. Okay, so you use the back EMF equal to negative L didt to find out the average induced back EMF. Calculate the maximum energy which is stored inside the inductor. You know that the energy is half Li squared. So if you want the energy to be maximum, then you have to make sure the I is maximum. So the maximum current is 2 ampere. Okay, then you can get the maximum energy. The current that passes through an inductor of inductance 0.48 Henry varies with time as shown. Please plot the induced EMF in the inductor versus time. Okay, so once again you use E equal to negative L didt to find out the value of E in all the regions. Okay, for example, in this region, you know that didt is a positive value. And then you know that the EB is a negative value. In this region, I is a constant, so di equal to 0, so you know that the back EMF is equal to 0. At this region, you know that I is decreasing, so di dt is less than 0. So when it is multiplied with a negative sign, the EB is a positive value. Okay, so you will have to remember that di is the final current minus the initial current. And then dt is the later time minus the initial time. Okay, therefore you can get the EB for all regions. The current in the 80 mH inductor changes with time as Ti equal to T squared minus 4T plus 6 amperes. Calculate the magnitude of induced EMF at time equal to 0. Okay, so I is this. You differentiate it with respect to time. Therefore, you can get didt. And then you get the value of didt when the time equal to 0 second. Okay, so this sign is when. Okay, didt when t equal to 0 second. Okay, so you can know that didt equal to negative 4 ampere per second at time equal to 0. So you can get the back EMF. And then by using the same reasoning, you can get the back EMF at t equal to 4 seconds. A circular conducting loop is connected to a battery and a switch S. Immediately after the switch S is closed, the current through the loop changes at a rate of 15 ampere per second, and the EMF induced in the loop has a magnitude of 5 volt. What is the self-inductance of the loop? E equal to negative L di dt. Okay, so the back EMF is 5 volt. Di dt is 15 ampere per second. Then you can get L. You know that actually sometimes we ignore the negative sign. Okay, because I only want to get the value of the L. Okay, because the negative sign represents the Lenz's law, which means that it represents the polarity of the back EMF. So sometimes when we want to care about the magnitude, we straight away ignore the negative sign. Okay, this is quite common. Okay, a coil has a self-inductance of 3 millihenry. If the current in the coil is reduced from 25 ampere to 0 in 0.5 seconds, the induced EMF in the coil is, okay, this one. An inductor consists of 20,000 turns and radius 3.7 centimeter. If the length of the inductor is 0.45 meter, the self-inductance is, okay, just now you already learned how to derive L equal to mu naught n square A over L. Okay, then you know that the unit for the self-inductance is Henry. A solenoid with a length of 16 cm has a total of 400 turns of wire. Its cross-sectional area is 12 cm square and carries a current of 3 ampere. Find the self-inductance. Okay, you use the same formula. Calculate the magnetic flux through the coil. NV equal to Li. So you know that magnetic flux is phi only, okay, which is B dot A. And then when you are asked to calculate the magnetic flux linkage, you know that magnetic flux linkage is N phi. Okay, which is this. Okay, so you really have to remember that magnetic flux is B dot A, and then the magnetic flux linkage is NB dot A. Okay, which is equal to Li. A constant EMF of 1.04 volt is induced by a changing current in a coil of inductance 0.26 Henry. The initial current is 13 ampere. Calculate after 2 seconds of supplying the current in the coil. Okay, so EV equal to negative L di dt, and then di is the final current minus the initial current. dt is the final time minus the initial time. Okay, therefore you can get the final current. Okay, the final current I denote it as I2. And then please find the magnetic flux linkage in the coil. The magnetic flux linkage in the coil is NBA. Okay, I repeat one more time. Magnetic flux is phi. Magnetic flux linkage is N phi. Okay, so you can get the magnetic flux linkage, and then you have to remember that Weber is the unit for both magnetic flux and magnetic flux linkage. A current changing at a rate of 10 ampere per second flows through a coil of 500 turns produces a back EMF of 24.5 millivolt. Determine the self-inductance of the coil. Okay, so E equal to negative L di dt, and then sometimes you ignore the negative sign because you only want to find out the self-inductance. Okay, you know that the self-inductance cannot have a negative value here. The magnetic flux through each turn when the current is 4 ampere. Okay, so you use N phi equal to Li. Okay, so you can get the value for phi, which is B dot A. A solenoid of length 2 meter has 1,500 turns. The cross-sectional area of the solenoid is this. Please find the self-inductance. Okay, you use the same formula. An air core long solenoid of length 8 cm and diameter 10 cm is made of 30 turns per centimeter. A current is flowed and increased to 1.5 ampere in 0.5 seconds. Okay, so please determine the induced EMF in the solenoid. E equal to negative L di dt. And then you know that the self-inductance for the solenoid is mu naught n square A over L. Mu naught is 4 pi times 10 power negative 7. N is what? N is the total number of turns in the solenoid. Just now you already know that it states that the number of turns is 30 turns per centimeter. And then you know that the solenoid is of length 8 centimeter. So your total number of turns is 30 multiplied 8, which is equal to 240 turns. Okay, and then the area of the solenoid is pi r square. Okay, and then the length of the solenoid is 8 centimeter, and then di dt is final current minus initial current divided by the time taken. Okay, so you can get the back EMF, and then you ignore the negative sign. State the effect on the induced EMF in an if an iron rod is inserted into the solenoid. The iron rod increases the magnetic flux density so that a higher EMF is produced. Okay, so you know that when the iron rod is inserted, you use mu R, mu naught instead of mu naught. Okay, and then mu R is a very large value for iron. Therefore, you know that the magnitude of the back EMF is getting larger and larger. Okay. An inductor of length 0.2 meter consists of 200 turns and cross-sectional area of 2.5 times 10 power -4 meter square. If a current of 1.2 ampere flows in the inductor, find the energy stored in the inductor. Okay, the energy stored in the inductor is half Li squared, and then L is mu naught n squared A over L. The energy stored in an inductor is mu naught when a constant current flows through the inductor. While maintaining the cross-sectional area, the two ends of the inductor are pulled until the length of the inductor is twice the length of the original inductor. Please find the energy stored inside the inductor. You know that energy stored is half Li squared, and then L is mu naught n squared A over L. So you know that the energy stored is inversely proportional to the length of the solenoid. So when the length becomes double, the energy is halved. A light bulb which glows with a steady brightness in a circuit containing a coil is shown. Okay, so the moment you see the word coil, you know that it is an inductor. Okay, so when you see bulb, you know that the bulb is just a resistor. Okay, because the bulb of course has some resistance. And then when you see coil, that means that when you see the inductor, you know that there's some back EMF. Okay, and then the back EMF has an opposite polarity with the EMF of the battery. Okay, explain the changes in the brightness of the bulb that could occur when an iron core is inserted into the coil. As iron core is inserted into the coil, the magnetic field by the coil increases, so the magnetic flux of the coil changes. And then you know that from the Faraday's law, the EMF induced is directly proportional to the rate of change of magnetic flux linkage. So whenever there's a change of the magnetic flux linkage, there must be some induced EMF. The direction of the induced EMF is opposite to the EMF of the battery. Therefore, the total potential difference in the circuit is reduced so that the current decreases. The brightness of the bulb decreases, okay, because V0 minus EB equal to IR. Okay. Actually, this is exactly the same equation that you use in the direct current motor, right? Which is in the 7.3c video. Okay, so if there is no back EMF, the I is very large. But then when there's a back EMF, the I is very small. A coil with inductance of 2 Henry, resistance of 5 ohm, and a switch are connected in series to a 12-volt battery of negligible internal resistance. The switch is closed and the current in the circuit builds up until it becomes steady. At the instant when the current is 1.4 ampere, please determine the back EMF in the coil. Okay, so you know that the coil has some inductance and also has some resistance, and then it's connected to a battery with the EMF 12 volt. Actually, of course, you can imagine this to be like this, right? That means that you imagine the coil to have no resistance and then it is connected in series with a resistor of resistance 5 ohm. Okay, then you still remember what is Kirchhoff's second law? Kirchhoff's second law states that the sum of all the potential change inside a closed loop of a circuit is equal to 0. Okay, so the Kirchhoff's second law says that E0 minus back EMF equal to IR. Okay, and then you can find the back EMF equal to 5 volt. So please find the rate of change of current in the coil, E equal to L di dt. When you get the back EMF, that means that when you get the induced EMF, and then you know that the self-inductance is 2 Henry, then you can find di dt. Okay. So in the next video, we'll be talking about the mutual inductance. Thank you.